Welcome to This Explainer. I'm honestly so pumped you're here today because we're going to do something that feels a little bit like magic. We're going to uncover the completely invisible, incredibly hyperactive world of microscopic particles that literally powers all the everyday stuff around us. Have you ever just looked around and wondered what's really going on behind the scenes? Well, today we're building a bridge. We're going to connect the big things we can easily see with the tiny, chaotic things that we can't. To get our minds in the right gear, let's play a little imagine if game. Imagine if you could zoom in like 1,000,000,000 times on the air right in front of your face. How would that hidden world explain the stuff we see every single day? Like, why exactly do those massive hot air balloons just magically float up into the sky? Or on a slightly more dangerous note, why does every single aerosol can, like hairspray or spray paint, have that big, scary warning label telling you it'll explode if it gets too hot? What is actually going on inside that metal can? To answer these questions, we've got to look at a famous quote from the legendary physicist Richard Feynman. He once said, "All things are made of atoms, little particles that move around in perpetual motion." Now think about that phrase for a second. Perpetual motion. The air around you right now, it's not empty space, not at all. It's actually the super dense, invisible swarm of trillions and trillions of tiny particles. And they never ever stop moving. They're zooming all around you, bouncing off you, and completely ignoring the speed limit. Section 1. Meet the invisible swarm. Okay, let's dive into this. In physics, to really understand how gases work, scientists use something called the ideal gas model. It's basically the ultimate rulebook for how these hyperactive particles operate. Rule number 1 is incessant random motion. That just means these particles are massive in number and they zip around in perfectly straight lines until they smack into something. Rule number 2. Point masses. This is really just a fancy way of saying these molecules are so unimaginably tiny compared to the vast empty space between them that we can basically pretend their physical size is practically zero. And rule number 3, which is definitely my favorite, perfectly elastic collisions. Imagine dropping a bouncy ball, right? But it never, ever loses its bounce. That's exactly what these particles do. When they crash into each other or the walls of a container, no energy is lost. They just keep ricocheting forever. Section 2. Temperature is particle speed. All right, I really want you to burn this mantra into your memory right now. Temperature isn't some mystical property. Temperature is just speed. Let's break down what that actually means. In our everyday macro world, we use a thermometer to measure temperature. But down on the micro level, it's really measuring kinetic energy, which is the energy of motion. So a thermometer is essentially just a microscopic speedometer. I mean, when you check the temperature outside, you're literally measuring how fast the tiny particles in the air are flying around. And this perfectly explains a rule scientists call Charles's law, which simply says that as temperature goes up, volume goes up. Let's see what that looks like in the real world. Think about a normal rubber balloon. If you put it in a really cold environment, the invisible gas particles trapped inside are moving pretty sluggishly. Because they're slow, they don't hit the inside walls of the balloon very hard, so the whole thing kind of shrinks and deflates. But take that exact same balloon and put it in a hot environment, suddenly you've given those particles a massive speed boost. They start ricocheting frantically, violently slamming into the inside of the rubber, pushing those walls outward, and the balloon expands. And hey, this is exactly why hot air balloons rise. By heating up the air inside that giant canopy, the particles move so incredibly fast that they spread way out. This makes the air inside the balloon less dense and literally lighter than the cooler air outside. Boom, you are flying. Section 3. Collisions create total pressure. Okay, get ready for your second core mantra for today's explainer. Pressure is just collisions. Forget everything else you might have heard about pressure. It's simply the combined feeling of 1,000,000,000 tiny microscopic slaps against a surface. Let's break down how this actually works into 3 simple steps. Step 1 is the approach. A tiny gas particle flies toward a wall. Step 2 is the impact. It smashes into that wall and bounces off perfectly elastically, creating this tiny, microscopic, practically unnoticeable force. But step 3 is where the real magic happens, the aggregate swarm. When you have billions and trillions of these tiny impacts happening every single fraction of a second across every square inch of a surface, all those tiny microscopic slaps add up into one giant, continuous aggregate force. And that aggregate force is exactly what we call pressure. And this brilliantly illustrates how, when a particle bounces, that perfectly elastic impact creates a change in momentum, generating a tiny bit of force. Now apply this idea to your family's car tires. Have you ever noticed that after driving on the highway for like an hour, the tires feel way harder and the pressure gauge actually reads higher? Why does that happen? Well, the friction from the road heats up the tires. And what did we say heat is? Speed. So the trapped particles inside the tires start flying around so much faster, crashing into the inside walls of the rubber harder and way more frequently. More collisions mean more pressure, leaving you with a rock-hard tire. We also use this exact same principle to our advantage in the kitchen. Think about pressure cookers. When you boil water inside a tightly sealed pressure cooker, you're creating a massive amount of incredibly fast hot steam particles. And because that lid is locked down tight, these fast particles are completely trapped. They furiously collide with the walls of the pot and the food inside, building up immense pressure. This high-pressure swarm literally forces heat into the food faster, cooking a tough roast or a pot of beans in just a fraction of the normal time. We're essentially trapping a high-speed swarm and forcing it to do our cooking for us. Section 4. The danger of heat and pressure. So what happens if we trap these high-speed particles in a container that absolutely, positively cannot expand or vent no matter what? To figure that out, let's look at the master equation that rules this invisible world, the ideal gas law. It basically tells us that pressure and volume are directly tied to the number of molecules and their temperature. So if the volume, the V, is a fixed, rigid metal can and you crank up the temperature, the T, the math demands that the pressure, the P, absolutely has to skyrocket to balance the equation. This incredible synthesis of our observable macro world with the invisible micro world perfectly explains our second question from the very beginning, why heating an aerosol can is incredibly dangerous. An aerosol can is a fixed volume. If you accidentally leave it in a hot car, or worse, throw it in a fire, the temperature skyrockets, and as we know, temperature is speed. The trapped particles start flying around at supersonic speeds, creating violent, extreme collisions against the inside of the metal can. Because the metal can't expand like a rubber balloon does, that aggregate collision force eventually becomes stronger than the metal itself, and boom, the can violently rips apart. Section 5. Why perfume takes time. Now, you might be wondering, if gas particles at room temperature are zooming around fast enough to cause explosions when trapped, shouldn't you smell a pizza being delivered or somebody's perfume instantly from across the room? The answer lies in a really cool concept called the mean free path. Yes, perfume molecules are traveling at a blinding speed of about 500 meters per second. That is literally faster than a commercial jet airplane. But they aren't alone out there. The air is densely packed with billions of other particles. So because of their physical size, the perfume particles can't just travel in a straight line. They suffer billions of crashing deflections every single second. This creates a jagged, zigzagging path that scientists hilariously refer to as the drunkard's walk. So they are moving incredibly fast for sure, but they're taking the absolute most complicated, chaotic bumper car route possible to finally reach your nose. Section 6. The macro-micro synthesis. So, what we've really learned today is that the big observable phenomena we see in our macro world are nothing but a direct result of the tiny, chaotic micro world. Before we wrap up this explainer, I want you to lock in those core mantras we built together today. Number 1, temperature is just speed. When things heat up, the invisible swarm is just hitting the gas pedal. Number 2, pressure is just collisions. Every push, every pop, every single tire gauge reading is just the aggregate slap of billions of tiny impacts. And finally, all the neat, predictable macro rolls of our everyday world are entirely powered by absolute micro-chaos. So, I'm going to leave you with this final thought. Physics isn't just a bunch of boring numbers on a chalkboard. It is the active, bustling reality happening right in front of your face. Next time you accidentally pop a balloon, check the air in your bicycle tire, or suddenly smell a delicious pizza from down the hall, I want you to stop for a second and ask yourself, what is the invisible swarm doing right now to make that happen? Thank you so much for joining me on this explainer. Keep asking those big questions and never stop exploring the incredible physics playground all around you.